Okay, so you said your instinct was to reflect over y equals x, and your motivation there was, if I heard you right, was you were looking at this function and you realize that if you were to just say reflection xy equals yx, and we'll worry later about what line allows reflections to work like that, then the function clearly has odd symmetry in that way, because f of yx, in other words, f on the reflected point, would give you, substituting carefully, y e to the x minus x e to the y, and sure enough, that is exactly the negative of f of xy. So your instinct is good there. You've found a hopefully this is a reflection, because if it were, then this function's got odd symmetry, and then we're halfway to a symmetry argument. So is this a reflection actually? And yeah, here's the reason why. If you have a point x comma y, well, that means that's x and that's y, and if you reflect this over, if you reflect it over this line, right now I just appealed to your geometric intuition. It's if that was x, then on the reflection that's x, and if that was y, then the reflection that's y, and that makes this point y comma x. Yeah, so the reflection of xy is yx.
So you're reflecting over the line y equals x.
The line is y equals x. That's right. Okay, now we're halfway there, right? So we have a line reflecting over which makes the function odd, but we've got to start worrying about the domain. And again, is a nasty little problem that very often students are so happy about having found a symmetry of the function that they forget to worry about the domain. Now, okay, y equals e to the x. Here, let me switch colors. Y equals e to the x. All right, well, that's something like that. X equals e to the y. Well, that's what we get from the other by replacing x with y. So that is a reflection over the line y equals x.
Log of x.
Yeah, it's also natural log of x. That's right, absolutely. Yeah. Okay, so that's looking good so far. Now let's see, x plus y equals 0. Well, that's that. And then let's see, x plus y equals 1. That's going to be like that. And, again, now, you don't have to make these arguments algebraically. You can just make the geometric argument and observe that, well, yeah, then look, you look at our domain here, and it's symmetric over that line, the same line. Now, you can make an algebraic argument. It's not that big of a deal. If you wanted to ask what happens when you reflect that line, x plus y equals 1, well, you replace y with x and you get 1 plus x equals 1. You get the exact same line.
Yeah.
Right? But anyway, on these kinds of questions, you don't have to flesh out the geometry argument about the domain. You just have to be right. And that is the catch, right? You're not responsible for the argument, but you are responsible for being correct. Yeah, sure.
So I wasn't sure how I could know if that was actually reflection from y equals x.
Say again?
I wasn't sure how to say if that was at y equals x, if the domain was a reflection, or
if the domain's symmetric.
Yeah.
Well, okay. So you're welcome to just make a geometric argument. If you don't see a geometric intuition for it, then the argument would go like this, and you would say, let's look at this curve here, for example. That's x plus y equals 1, right? And reflecting, you replace x and y with y and x, and the process then, when you reflect this line, you get y plus x equals 1, and conveniently that equation and this equation are equivalent, right? So, and then likewise for x plus y equals 0, same deal, right? So yeah. Right. Okay, so yeah, the integral is 0 by symmetry, right? Is everybody happy with this one?